Hello everyone. And welcome back once again to another interesting video. In today's video we'll discuss the nuances of machine learning and deep learning, unraveling their core concepts, applications, and key distinctions. So if you are ready, let's start today's video. In the rapidly evolving landscape of artificial intelligence, two terms that have gained immense prominence are machine learning or ML and deep learning or DL. These technologies represent pivotal advancements in the field, offering solutions to complex problems and pushing the boundaries of what computers can achieve. In this comprehensive exploration, we will delve into the nuances of machine learning and deep learning, unraveling their core concepts, applications, and key distinctions. Understanding machine learning. At its essence, machine learning is a subset of artificial intelligence that empowers computers to learn from data without being explicitly programmed. The driving force behind ML is the concept of algorithms, sets of instructions that enable machines to recognize patterns, make decisions, and improve their performance over time. ML algorithms can be broadly categorized into three types: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning. In supervised learning, the algorithm is trained on a labeled dataset, where each input is paired with its corresponding output. The model learns to map inputs to outputs by generalizing patterns from the training data. This approach is commonly used in tasks such as image recognition, speech recognition, and classification problems. Unsupervised learning. In unsupervised learning, the algorithm is provided with unlabeled data and tasked with finding inherent patterns or structures within it. Clustering and dimensionality reduction are common applications of unsupervised learning. This type of learning is valuable in scenarios where labeled data is scarce or expensive to obtain. Reinforcement learning. Reinforcement learning involves training a model to make sequences of decisions by interacting with an environment. The model receives feedback in the form of rewards or punishments based on its actions, allowing it to learn optimal strategies. Applications include game playing, robotics, and autonomous systems. Applications of machine learning. The versatility of machine learning is evident in its myriad applications across various domains. 1. Healthcare. ML is utilized for disease diagnosis, drug discovery, and personalized medicine. Predictive models can analyze patient data to identify potential health risks and recommend tailored treatment plans. 2. Finance. In the financial sector, ML algorithms are employed for fraud detection, risk assessment, and algorithmic trading. Predictive analytics aids in making informed investment decisions and managing portfolios. 3. Natural language processing or NLP. NLP, a subfield of ML, focuses on enabling computers to understand, interpret, and generate human language. Virtual assistants, sentiment analysis, and language translation are common applications. 4. Image and speech recognition. ML powers image recognition systems that can identify objects, faces, and scenes in images. Speech recognition technologies, such as those used in virtual assistants, rely on ML algorithms to understand and respond to spoken language. Now, let's understand deep learning, a subfield of machine learning. Deep learning, on the other hand, is a specialized subset of machine learning that involves neural networks with multiple layers, deep neural networks. The term deep refers to the depth of these networks, characterized by a hierarchy of interconnected layers, each responsible for extracting increasingly abstract features from the input data. Neural networks and deep learning architecture. At the core of deep learning are artificial neural networks, inspired by the structure and functioning of the human brain. These networks consist of layers of interconnected nodes or neurons that process and transform input data. The key components of a neural network include: 1. Input layer. The first layer that receives the raw input data. 2. Hidden layers. Intermediate layers between the input and output layers where the actual computation and feature extraction occur. Deep neural networks have multiple hidden layers. 3. Output layer. The final layer that produces the model's output. 4. Weights and biases. Parameters that the network learns during training to optimize its performance. Training deep neural networks. The training of deep neural networks involves feeding them with labeled data and adjusting the weights and biases to minimize the difference between the predicted output and the actual output. This process, known as backpropagation, utilizes optimization algorithms to iteratively update the model's parameters. Key characteristics of deep learning. 1. Feature learning. Deep learning excels at automatically learning hierarchical representations or features from raw data. Each layer in a deep neural network learns increasingly abstract and complex features, allowing the model to capture intricate patterns. 2. Representation learning. Deep learning enables the automatic extraction of meaningful representations from data. This ability is crucial for tasks such as image and speech recognition, where the model learns to represent high-level features. 3. End-to-end learning. Deep learning models are capable of end-to-end learning, meaning they can directly map input data to output without relying on handcrafted features or intermediate representations. This is particularly advantageous in complex tasks. Applications of deep learning. Deep learning has witnessed remarkable success in a wide range of applications, transforming industries and setting new benchmarks in performance. 1. Computer vision. Deep learning has revolutionized computer vision, achieving unprecedented accuracy in image and video recognition. Convolutional neural networks or CNNs are particularly effective in tasks like object detection and image classification. 2. Natural language processing or NLP. Deep learning models, such as recurrent neural networks or RNNs and transformers, have significantly advanced the capabilities of NLP. Applications include language translation, text summarization, and sentiment analysis. 3. Speech recognition. Deep learning algorithms power state-of-the-art speech recognition systems, enabling accurate transcription and voice-controlled applications. 4. Autonomous vehicles. Deep learning plays a crucial role in the development of autonomous vehicles, where neural networks process sensor data to make real-time decisions in complex environments. Key differences between machine learning and deep learning. While machine learning and deep learning share commonalities, several key distinctions set them apart. 1. Representation of data. In traditional machine learning, feature engineering is a critical step, where experts manually select and design relevant features for the model. Deep learning, however, excels at automatic feature learning, allowing the model to discover intricate patterns from raw data. 2. Complexity of models. Deep learning models, with their multiple layers, are inherently more complex than traditional ML models. This complexity enables deep neural networks to handle intricate tasks but also requires substantial computational resources for training. 3. Amount of data. Deep learning models often require large amounts of labeled data for training. This is in contrast to some machine learning techniques, such as decision trees or support vector machines, which may perform well with smaller datasets. 4. Interpretability. Machine learning models are generally more interpretable than deep neural networks. The black box nature of deep models can make it challenging to understand how they arrive at specific decisions, raising concerns in applications where interpretability is crucial. 5. Training time and resources. Deep learning models, especially large ones, demand significant computational resources and time for training. Traditional ML models may be more computationally efficient, making them more suitable for certain applications with resource constraints. Challenges and considerations. Both machine learning and deep learning face challenges and considerations that impact their effectiveness and adoption. 1. Data quality and quantity. The performance of ML and DL models is highly dependent on the quality and quantity of training data. Inadequate or biased datasets can lead to suboptimal models and biased predictions. 2. Interpretability and explainability. The lack of interpretability in deep models raises ethical and practical concerns, especially in sensitive applications like healthcare or finance. Understanding how a model makes decisions is crucial for trust and accountability. 3. Computational resources. Deep learning models, particularly those with numerous layers and parameters, require substantial computational resources for training. This can be a barrier for smaller organizations or research institutions with limited access to high-performance computing. 4. Generalization and overfitting. Ensuring that a model generalizes well to unseen data is a common challenge in both ML and DL. Deep learning models, with their increased complexity, are prone to overfitting, especially when training data is limited. 5. Transfer learning. Transfer learning, the ability of a model to leverage knowledge gained from one task to improve performance on another, is a crucial consideration. While transfer learning is effective in certain scenarios, it requires careful adaptation and tuning. Conclusion. In conclusion, machine learning and deep learning represent two pillars of contemporary artificial intelligence, each with its strengths, applications, and considerations. Machine learning, with its diverse algorithms and interpretability, continues to be a versatile tool in solving a wide array of problems. On the other hand, deep learning, powered by neural networks, excels in tasks that demand automatic feature learning and the processing of complex data. The choice between machine learning and deep learning depends on the nature of the problem, the availability of data, and the computational resources at hand. While both technologies contribute significantly to the advancement of AI, it's crucial to approach each with a nuanced understanding of their capabilities and limitations. As the field continues to evolve, the synergy between machine learning and deep learning is likely to lead to even more sophisticated and impactful applications, reshaping the way we approach challenges and unlocking new possibilities in the realm of intelligent computing. That's all for this video. If you found this video helpful, don't forget to subscribe, give it a thumbs up, and hit that notification bell for more content, so you don't miss any upcoming video. And, if you have any questions or topics you'd like us to cover in future videos, please let us know in the comments below. Until next time, keep exploring and keep coding. Thanks for watching, and happy coding.